So hopefully today we will get some information.
Yes.
Because we need to put them somewhere tomorrow. Okay. So we'll wait for Dima and Bowen. So Bowen is here. Okay, so if this is not Dima, I will start. Okay. So the topic of today's talk would be the formation of topological quantum field theory Saskin mechanism in examples. So actually I will not ask about it on the exam. I'm just giving this lecture to let you know about this phenomenon. So it started with Edward Newton. Who said, suppose we have topological quantum field theory. Suppose we have observable O0. then what can we say about D of O0? She said that D of O0 is Q of O1. We had it in our AKSZ construction because in our AKSZ construction, remember, we had this formula. Plus, there was another term. So D, now let us imagine that there is no other term. Let us imagine that we have just this formula. Suppose we have a function f of phi. Let's consider this f of phi 0. You may easily check that Q of f phi 0 equals to 0. Because Q is a bracket with respect to S. So what does it do? It takes derivative with respect to phi and multiplies it into d phi. So Q applied to phi 0 is 0. Q applied to phi 1 is d phi 0. So that's how it's worked. So that's how it was working in AKSZ. But it's not AKSZ formula that I'm going to explain to you right now. I'm going to explain to you more generally. Then we can say d of O n of d minus 1 equals Q of O. So these are called Witten's different equations. And then he said, well, in this particular case, I can deform a correlator by exponential over xd in d-dimensional theory of all these. So the elements are parameters of the formation. Then we can argue what happens in this particular case. If I take Q applied to psi, and here I put this deformation. Naively, Q applied to all is D minus 1. So naively, I might think and this is the total derivative, and this total derivative integrates to D. But I put here naive. Really, there could be singularities. So if I expand this exponent, I would have something like Q star. And if I take this point P0, I should better cut a small disk around P0. Then when I take Q out of this psi here, I will get psi at pi0 integral and here I'll get d of d minus 1. And it is not zero because the result would go to the boundary. So if there is a singularity, I cannot ignore this there. So it is not Q of psi that decouples. It is Q plus K minus. In the beginning, or does it in here? Okay.
Here in the last line, is this OD, not OD minus 1?
So here is OD minus 1.
You write
I am integrating. Yes. So it was OD integrated. I'll draw a picture.
Actually, I don't quite understand why we assign D and D minus 1 both to those observables and to the integrating domain.
So
what's the meaning of D?
Of this D, the meaning of D is dimension.
Dimension of observable, like degree of observable.
D is okay. All D belongs to the D forms.
So you use XD to mean XD means the
XD means the D-dimensional space.
okay. So there's only one space, right?
Only one space.
D.
So this space is XD minus D pin. This is the point pin.
Yes.
And I'm studying decoupling of the observable Q on T.
Sorry. You use Q as an operator, which has some relation. Like just Q is like drum different,
Yes.
right?
But so Q is an operator on the space of fields. And I assume that Q of O D is not zero. It's totally, so this is the run, not this D. I'm sorry.
Yeah.
And then I said that naively, if you study this correlator, you may think that Q exact terms decouple. Why they decouple? Because I can take Q out of psi and bring it here. I'm bringing it here and I'm getting the total derivative. Okay, I say that I am integrating over space xt of the total derivative and naively it is zero. However, I need to be accurate. Namely, I have an insertion at point P naught. That's why I cannot say that I integrate over xt because there could be singularities in correlator between OD and something at P naught. So I cut out the small disk of radius epsilon. And I run the argument. And when I run the argument, I take Q, act on OD, have a total derivative, but integral is on the space that has a boundary, this boundary. So boundary itself is small. However, if there is a singularity in correlation between this O and this psi, even small boundary can give a non-vanishing contribution. So that's why this is the result. It's an integral over the boundary of the disk of psi at pi 0, and here I have OD minus 1. So actually, it's not Q of psi that decouples in the first order deformation. So what decouples is Q of psi minus T alpha of D minus 1 psi. This is what decouples. So we say that, well, current generating Q is reported to J plus However, now we meet with a new problem. We assumed that Q square goes to 0. What can we say for this new current, GT? And here I put a question mark. So to the first order, everything is okay. And here I see an obvious problem. Here is gamma, where I integrate all alpha v minus 1. Here is the gamma that is homotopic to it. And I also integrate all alpha v minus 1. I need to check that this squares to 0. How can I do it? I'm trying to move this gamma through this gamma prime. It would correspond to taking a square. However, now please be patient. Let me take a point on the contour gamma prime. I have a contour to the left, and I have a contour to the right. I want to move this contour to this contour. So the difference is a contour going around the point on the second contour. So this contour is gamma 1, this is gamma 2, this will be gamma 3. This is gamma 1. So this is gamma 2. And I fix a point P2 on gamma 2. And I'm moving gamma 1 to gamma 3. And I have this particular linking between the contour and the point. And I still need to integrate this linking over the contour gamma. And this is an abstraction. In the following topological quantum system. And actually, this abstraction is a boundary anomaly. You may ask, what kind of boundary I met here? The answer is the following. You have 2x. And you have 2 points, P1 and P2. And you think that you integrate this type of correlation. However, these points P1 and P2 actually meet at diagonal. So you need to cut out the diagonal and the boundary around the diagonal. And schematically decompose it in the following way. So there is a boundary in configuration space where P1 could be everywhere on X. P2 is the boundary of the epsilon disk. And this is the band configuration that we have.
And this is called boundary anomaly. And now in advance, I'll tell you that sometimes it's possible to cancel this boundary anomaly by what is called Fishler-Susskind mechanism. So how can I cancel it? There are several ways to cancel it. One of the ways to cancel it is if boundary anomaly it says if you of something so if boundary anomaly is Q of something, and let me call it Fishler-Susskind, then I would say that this theory has no anomaly. Boundary anomaly coming from here. So how would I get this boundary anomaly coming from here? I act by Q. Action by Q gives me, it sends me to the boundary of the configuration space. Boundary of configuration space is the position of a point and the point around it. And that's the boundary anomaly. But suppose it is Q of some other term. Then I just add this term. So when I act by Q, Q of Fishler-Susskind term would cancel me this anomaly. And I will have anomaly-free theory. And this is the condition for the forming of a topological theory. Boundary is cancelled by something that is Q. Exact. And then, of course, you may ask, what is the abstraction? Abstraction is, of course, the class of boundary anomaly in Q cohomology. It is the abstraction. By the way, how to check that boundary anomaly is actually Q closed? Okay, it's possible. So boundary anomaly is integral. No. It is a space. So how to draw it? 1 second. So actually, when I act by Q here, I will get V of something. Okay, so there is, I'm sorry, there is more general argument. More general argument works like this. There is a configuration space where we subtract the edges. So boundary anomaly is the following. You take a boundary of the configuration space. And then you integrate over the boundary of configuration space all times O. Now you apply Q to such construction. It is the same as to apply Q here and here. Now, Q applied to O is actually D applied to O. And the same is here. So altogether, you have integral over the boundary of configuration space of D of something. And this is definitely equal. Okay, so this is very abstract term. And I understand that what I explained was abstract. But here I said that we will study it in examples. And now, after I gave you this abstract treatment, I will come to particular example. And particular example would be
Topological quantum mechanics. On S1. So with the case one has Hamiltonian H, that is QG plus. And then there is observable O0 such that Q O0 in data equal to 0. Now, G of O0 under correlator is H applied to O0 under correlator. And let Q applied to G plus O0 under correlator. So O1 is nothing but G plus related. You may always think about G plus as having VP with it. So here I modify it. Just to show you that O1 is actually a 1-4. Okay.
May I ask a naive question? Why D O0 is H and
By what?
D O0? The
Why
first time.
DTO0 is H? It's called Heisenberg equation. Okay? O of T. The relator of O of T is what? In this case, maybe I'll write you another formula, not this one. 1 O T2 on the third time T equals, you start with 0, then you evolve to Hamiltonian H. So this is the definition of the correlator in quantum mechanics. You have starting point 0,
you have points 1, 2, and the total time is t capital. This segment corresponds to e to the t h, and then you have an insertion of operator, then you have t2 minus t1 h, then you have insertion of operator, and then these lengths so here I have points and lengths of the arcs.
But I guess there are only 2 points. The T1 plus
Yes,
T1
yes.
plus.
But there is a 0 point where in some sense 1 is inserted. So the origin of coordinate. And then d over dt1 comes from 2 terms. From this term and from this term. And this is called Heisenberg equation.
So originally you write something like DO0.
Yes.
Then you use dt d over dt of O0.
Yes. So what I did, I wrote DO0. So it is dt. In this case, it's dt1, dt1. So it is HO1, and I have also dt1. Then I took H and I made G out of it. So this example is as explicit as it's possible. So you may consider Q and G as just finite dimensional method. Okay? So here I have O0 and O1. And now I'm trying to deform the thing. Since I already have T, I'm sorry, I will deform it with parameter G. So it is a naive deformation. So here I integrate. And now, since O alpha 1 is G plus O0, I have what I naively expected at the first order. So in the first order, O1 dt now, what is this O alpha 1? It is D plus O0. Well, and now observation. If I change Q to Q plus G alpha O alpha, then Hamiltonian would be changed to H plus G alpha G plus O alpha. Now, what would happen to the e to the th? There is a very famous formula. What happens with the e to the th when you change h? I write here G alpha I will write here just not G alpha, I will write here just O1. So if I change Q like this, so look what I'm doing. Before I said I will change correlations and it will correspond to some change of Q. However, it is easier for me to do all the way around. What would happen if I change Q? If I change Q, I am getting this shift of e to the th. Now I will come to Bowen's example. So what I'm going to show? I'm going to show that such change of Q actually corresponds to so that's what I'm going to show. So in one, I changed Q and changed Hamiltonian corresponding to one. Here, I'm changing correlate. So how can I show it? Let me consider some psi here. I'll do something simple. Let me consider correlator of psi of 0. And let me make this Q to Q plus G alpha by not change here. This would be psi 0 So I changed Q. And it corresponds to e to the e capital A plus G plus phi naught T. Now I will use this magic formula. In the first order. So here it's correlator, and here I will write supertrade. Plus, and here I will use this formula. I'm using this formula now. Now I see that what is written here. So the second term is nothing but integral over dt prime from 0 to 2 of what? Of correlator of O of 1 at a point d prime time at point 0. Because I just explained to you what is the correlator in quantum mechanics. And this is a purely mathematical formula. So altogether it is psi plus g alpha because this is all one alpha. So I started with the formation of Q, and I said, and I showed that it corresponds to such deformation of the correlate. So this line is trivial, but it is still to the line. And you may check all steps here. Now, interesting phenomena. Interesting phenomena is Q G alpha, that is Q plus G alpha pi alpha naught may not square to 0. Actually, QG alpha squared equals this squares to 0, this is 0, plus G alpha G beta So it means that we started with a topological theory, and in topological theory, it's very crucial that Q squared it to 0. And in the second order, we got a problem. I'll call it anomaly. The right-hand side of another equation is your model. From this presentation, it is obvious. Q kills pi alpha 0, so it kills their commutator. Later, we will interpret this phenomena as a phenomena of closeness of boundary contribution. But at the moment, let us just observe.
Yes, excuse me. Here, so G doesn't contain any degree. G is
No, G is just formal parameter.
so we know because it is phi alpha 0 are all 0 form, are even.
Yes, so G's are formal numbers.
Yes.
Okay, look, that's what we are doing. This is a one form. And this is just a number. Parameter of deformation.
Yes, but in this case, because phi 0 they are 0 form, so G alpha, G beta, if we assign them to be odd number.
So they are zero forms, they are just operators.
Yes, so their anti-commutator is not simply 0.
It's not zero.
Yes, but you see here, G, if we assign G alpha to be odd formal number, then this Q square.
So if you like G alpha to be odd, then here you will have commutator. You may play these games, but I prefer to play game where G alpha is. I would like to read here G alpha even, G alpha odd. So it's a classical case where we have an ordinary deformation space of theories.
I don't quite understand. You previously said 0 refers to 0 form. This.
Yes, this 0 refers to 0 form.
Then 0 form we can understand it to be even.
You see, it is a 0 form as an element of the space of forms on a circle. But it is also an operator. The parity of operator comes as a sum of parity of the spaces where it is active.
Yeah.
Okay, let me give you, so it was an example, and let me give you an example of an example.
So this 0 will be something like in the source space theory. Like you can have some
Yes.
target space. This is
Yes,
an operator.
yes. So example of an example. Example of an example is that quantum mechanics is the space of states differential form from some manifold X. Q is, I'm sorry for this. Q is this D. So I have too many D. There are. And let me take as D plus U to D. Maybe I would prefer not U to D. I will do it later. Then Hamiltonian with operation. And then what would be phi naught? Log 1/4. Okay, I will do some. So the space of states, the space of the differential forms on some manifold, okay, fine. I already have it. Times some W is a vector space. So Q is just the RAM in Y. I take metric and I have G plus. So Hamiltonian is this.
Phi 0 is 0 form, right? Closed.
Closed one forms on Y. on the target.
Oh. So here, y is the same as S1.
Why is the target?
Oh.
So this model corresponds to the maps of F1 into Y.
So phi 0 also contains some t parameter, sigma parameter. I mean the S1 parameter.
Phi 0 is not containing T parameter.
So phi 0 is a form one target, so you can pull back it to S1.
So phi 0 is an operator in this space.
Yeah.
If you have a one form, multiplication by one form is an operator in this space. And this operator is closed under the action of this Q. And this is an example of an example.
Sorry, this O0 and O1, they are like forms on source space.
Yes. Yes. So O0 is an operator on the source space. It is this one.
But phi 0 is on target.
Phi 0. Phi 0 is an operator that is made out of the form on the target. So maybe this example is not simple enough. I'm thinking, could I make it even simpler?
I mean, because this O's contains some T inside. T is like S1.
O0 contains no T because it's an operator. There is also the concept of correlator. And here we discussed what this means. So this is a concept of correlator. Correlator contains T's inside. There is a concept of an operator. Operator does not contain T inside. In order to make correlator of an operator, I'm running this procedure.
Yeah, I see. So O0 is like a constant source, but I mean, it has no T, but
You cannot say that it is a constant on source.
Okay.
I'm thinking where to write.
Before you see the O1. O1 has dt. It's
Yes.
defined like dt g plus.
Yes. So once again,
Okay.
O0 belongs to endomorphism of the space of O0 of T. There is a constant correlation of O0 at point T. And it is super tricky. Here you have an operator, no dependence on it. Here you have a correlator. Correlator has a dependence on it. We say that an operator has correlators that depend on T defined in this particular way. Now, there is O1. So to avoid problems,
I will.
You see, O1 is just right on the right hand side. Here you just erase it. So
Still, if I run it this way, this is an open thing. Okay? It is natural. So, but we can study correlations of O1 at point T. So it is natural to multiply it by dt. Now, once again, there is an equation that Q applied to O1 of Q. So what does this mean? What does this symbol mean? It means that I take Q, I apply G plus of 0 and I put here raise e to the t minus t, e to the t minus t prime h. So when I use this symbol, I mean exactly this. So it means that I apply Q to O and place it at the point T. Now I commute here and I'll get that it is exactly d over G of what? Of Losev race of 0. And here I have to the capital minus t h. And here I have e to the t minus something. So this is d in t. So correlator of all of this. So I'm doing some clarification. So what I mean by this, what I mean by that. And these are standard notation in quantum mechanics, where people study separately operators, separately correlators, correlators depend on T, operators do not depend on T.
But at the moment, I have seen such interesting phenomenon that Q breaks. I would like to interpret this phenomena in terms of boundary of configuration space, as I explained. Here is just computation of correlate. Before I do it, I just want to say, look, sometimes I can solve my problem. If phi alpha 0, phi beta 0, is some C is Q of some C2, I can solve this problem, but let us do it after the break. Okay?
Q，这是什么意思？这个地方要带还是因为算它的第一笔翻译3倍，对，可以上翻译位置，可以用一个后面的翻译，这样子，这里这个是做。我那个人翻，我stop，翻就是翻，翻是翻，是翻，然后所以，然后你这个地方的话，变成这个，OK，这个是不要把这个展开写。这个上面是负，这个的话，我们是这个可能是。我能再请问一下，你刚刚是form 是前面往后面都得按什么？这个 S 的作用就是 S 作用来看。你现在是在算范群是吧？算它作用在就等下，你现在我现在比如说你要算什么 S 写群。所以这 phi star 就是 define， 就是算出来它就对吧？它可以对吧？我能算一下，就是这个东西，就现在要把这个东西和这个做那个东西就 S 做那个 side 做那个 side， 然后我现在要把这个 partial S partial phi。的 head star 乘上 partial psi partial phi head 加上 partial s partial phi head 还是在是 phi star，然后因为你说这个长这个形式，它算成优质地方，x， 这个地方是这个star，这样我这个是 phi star define， 你对这个 phi star 求到是吧？就概念，所以就是 define， 然后他对 phi hat 求到了没有？没有。phi hat 可能是define star。哦，因为就是你的意思是像是用了那个什么玩意儿一样，那个不是分布积分，就是这个 define 是算在一起的。这个形式里 define 算还是 phi define 这样子是吧？是 define 算在一起的，还是 phi 乘 d 乘 phi？ 它这个 d， 它这个 d 就是 source， 所以你这个 define 线是算在一起的。对，你别算到后面，你可以做分布积分把它算进去。也就是 define， 这有个正负号的问题，这个有个正负号，但是这个只有这个反正他错的那些 degree 是不是为了测这个地方？错 shift 和 degree 再说这个 AKSZ 的时候 shift degree 是不是想在这里测这个符号？啊。可能是，这符号我们也不管它了，不管上来就不管。然后这个地方它这里出来以后，到这儿，所以你，刚刚这个操作是这个概念以后是一个，所以是 define hat partial sine partial phi hat 这样，后面那个对，然后一个3是什么概？如果先写清楚的话，就是 define hat star 乘上这一项，就是你的意思是 percent 是跟 phi 有关 ，phi star 没关。如果你 percent 是这样是哦，就因为这个地方就是这个地方它是 phi 的话，这是 phi star， 所以这个东西就是这个做出来应该是 define hat，define zero define hat， 是吧？你可能跟我说最后他想是找成这样，对，是长这样，是啊，对。然后我们把这个 phi zero 带进去，咋算呢？但是要保留一个突破，保留一个超负保留，就是你这个 hash 规则都比如说偷放这个是比如说正常，也就是这个。就你现在不是按照这个在算，有具体用算，对，你现在就是说它 moral 的一下，它最后的一个东西，我在说啥？Q phi， 严格来说是负上。首先给它最后的分散上，其实这个比如说赛是在这一层，最后算出来应该会有这样的形式。这一层应该是是这个题说是 C 也是 source 上的一个对，然后因为你这里 其中你不是做那个计分嘛，做那个岛，你这个地缘是，就是地域岛，渔港，这个属于 bracket 分母这什么参数？其实应该是这个 bracket 的意思加 x 吧。没有也不会，这个是那个整个这个 x。如果你这个 bracket 是因为是对 5在 z 所，所以这个 bracket 就是这个 x 就是 z， z 的话就比 5， 这边 5 star 比 5， 然后对 5 z 组 star z 组，你就做出来这个是哪个是对吧 ？z 写到这里，
这三十哪个去了？不是这样，然后你这是什么？
所以就是这个 bracket 影响这些。要不就不需要说到。
这个是这个东西，
这个是
bracket
的，这个是 bracket， 这个是 x， 这个 s 对这个，对吧？代进这个表示一下，这一项题就是把这个 star 导掉之后，因为你在不同的 location 就是这嘛，这个写这个实际上它这个积分，然后你假设你没记出来，你要把它记出来的话，可能是要以这个通过。就是写这种形式，你就可以看出来最后算出来的形式还是有对上，还是要保留一个通过。
所以现在要 source 上套仿变 d 这个东西，这个
说 d by x 欧米伽，你最后只剩下就是这样，假设3，因为给它保留通过，然后给这个正方形不太一样，要是它的通过，现在你Losev说的是它开，它通过前面，把它写开的话就是。
你最后保证的是这个是 sigma 的通风，
就这个是错，
对，这整个是通风，然后
这个就是
对，
你要保留它通过，我不知道它的欧米伽万，但我猜这个要加个标，代进指标，然后你把它代进算，它是只有2，你要保留通过，第一次通过是，所以这个题，它这个题应该是那个，
这哪一类我们就这样写，就是可以投票。
我觉得它应该是这样一个外向，我觉得，
所以你觉得这个 form 还是 zero form， 这个还是 zero， 因为本来这个 zero 代表是 source 上后边，就你正常，如果是 target 上的 zero form， 你第一下在 target 这个 form 拉回来可以出，但你现在说的是
这个 D 指的是它的对 target 上的这个 define 完全不是 workflow。那行，那它 workflow 这个 workflow 然后你可以 OK， 现在是 OK， 就这个是 workflow，
现在你要证明它这个概念。
对，
然后你后面这个
这里才能
这个不一太是这个东西是这个东西。然后这个东西是一样的，因为它对它这个，它对它这个是一样的。
这个是什么意义？
这个
我们先在
它是这个的
什么意思啊？
它是这个的意思。
但现在这个 file 它是一个这是什么？就是一个 form， 还有 fallback，
我觉得应该不能。我觉得好。
对，它还需要 fallback， 然后再这样。就你的意思是它是这样一是一个推广。先用一下，
这是泛函数，这是泛函数，这是导数，这是普通的学法，这是泛函数，它们都有一个这样列函数的学法。
这个它这些玩意儿它，然后现在都是 form 是吧？find zero find at 然后 form， 还不是其次的 form， 就这个还有各种次数的 form。就是说我们现在这个在 form 这个空间上，我们把破败率变成一个 map， 从一个 source 拿到一个 target 上的 form 这样一个东西，然后变一下。OK， 反正这个地方我们是觉得是，然后这个就是form， 然后
这个就是这里面是，只是假设新发生，新发生的完。
但是你这个逻辑用在发问上是一样的。Yeah， 你让它这个是发的，还是区别一下？对，它是。
Okay, maybe I'll continue. Just imagine that this thing is exact. Then it means that I have a deformation. But it is easy to check that QRG is equal to 0. So it is all of GQ. And I may expect, so here I say that I may expect
Is a deformation of logical quantum theory to the order G squared. I actually have it from the operator point of view. This is actually QG G plus. But I would like to have another interpretation of this. I would like to have an interpretation of this phenomena in such terms that I could apply to topological quantum theories in arbitrary number of dimensions. So what is important here? I have an extra term. How can I explain this term? So I will raise with the word. And I'll do the same computation that I started with in this quantum mechanical example. And I will study it going forward. And everything is on this one. I am trying to find modification of this cube, an abstraction to modification of this cube. Trying to argue in terms of topological field theory that would go to any dimension. The data exponential correlates with the following. Here I have point T1, here I have point T2. Sorry, that's fine. O alpha,
of beta G alpha G. And this is the point zero. Where I have Q of beta. And what I actually want, I want the decoupling of Q of psi. So what does it mean to decouple Q of psi? Means to find Q tilde on psi such that Q tilde on psi inserted at point zero with these insertions integrated gives zero. It means decoupling. Previously, we studied decoupling when there was only one T1. And we found that there is always decoupling where Q tilde was Q plus commutator with over F with GL. Now we have 2 points. So we are playing the same game. We take Q tilde out of it. Sorry, we take Q out of this point. And here we will have integral over f1 times f1. And here we have O alpha 1 1 O beta 1 dt2. T1 lives here, T2 lives here. Now we use the fact that Q applied to O gives total derivative. And we also use the fact that we integrate over S1 times S1 minus diagonal. Because correlators could jump. That's why we cannot ignore it. So what is this? Q acting here gives
plus similar terms where alpha and beta are interchangeable. So what actually do we have? We have an integral, so S1 times S1 is this. Here is diagonal. I'm cutting the diagonal out. So here we have psi 0. And here we have total D over T. I think, should I do it in steps? Maybe it's better to do it in steps. In order not to make you afraid. So I have this term, and I have the second term. So what is it? It is an integral over of the total derivative of some differential form on the configuration space. You may ask, what is this form? You may say that it is d1, d over d1. You may say that it is this form, or you may say that it is another form. So these two forms differ by, so when I say that something is d of something else, I can add here a closed form. Let us take this. But you may ask, what about other terms? You see, because Q was acting here, and we got this term. And so my main statement is that here we are getting psi naught, and here we have d of some differential form on configuration space. So we integrate and when we integrate, we get psi naught, and together with this psi naught, we have an integral over the boundary of configuration space of this differential form that is O of T1 sub O of T2. 0, 1. Now, what happens with the boundary of configuration space? Boundary of configuration space contains of points where, okay, so here it's T2 that is running, where T2 is going to 0. But these are points that we like. Because if it's T2 going to 0, we will put it in the modification of the operator Q. However, there is an unpleasant term. Unpleasant term is the boundary in the configuration space where T1 hit T2. And we have this boundary contribution. We have O alpha G alpha, O beta G beta. We have G plus. And we are integrating it over dt. So what is this t? It's a coordinate on the boundary of configuration. So we have this term. And written like this, it is not a total derivative. So let me recall that here I have only one G plus. I had two G pluses because I had two moving points. When I got on the boundary of the configuration space, I lost one G plus. However, one G plus is still here, and here is an integration over this point. And we call it anomaly. How to cancel this? If G alpha of alpha, G beta of beta is not just Q exact, it is not just Q closed, but Q exact. I will put it here, and I will get integral of G plus Q of T2. And now I know what to do. G plus Q of C2 is nothing but I take Q out. It gives me A of C2. And since it is in this integral, I am getting a total derivative. And this total derivative comes to the initial point Q. So that's how it goes in quantum mechanics. And you may perform this computation.
So here O alpha, O beta, 0.
Zero, of course, zero.
So you mean we move this O1T2, the G plus out.
Yes, so 1G plus is out. So originally, integral was when I moved 2 points. When I took Q out, then it led me to D of some one form. This D of some one form was integrated over the tubular neighborhood of the diagonal. On the tubular neighborhood of a diagonal, I have this commutator. One integral is still left. So here I had moving of 2 points. So boundary knows position of 1 point. So I have this contribution of a boundary. And if this contribution of a boundary is not zero in Q cohomology, I am done. I don't know how to deform. But if it is zero in Q cohomology, I can deform. And I reproduce exactly the same phenomena as I had informal doing deformation of Q. And this is very general phenomena called Fishner-Susskind. Many deformations could be treated this way. Let us study type B2 on Y. Q was the bar operator of U. Observables were just polyvectors. And I tried to do the following. I tried to make such deformation. There are 2 points on sigma. And in the boundary, one goes around another. And boundary contribution was PP. And here we did bracket between solid vectors. And that is because in singularity you have a green functions. But then you ask when you can move it. And you do it by saying that here you have another polyvector. And this is called the Daniera-Spencer-Baranikov-Kontsevich equation. And the meaning of this equation is the cancellation of the boundary anomaly in the configuration space of points. Another example. You have a disk. That's how I'm drawing a disk. And you have points on the boundary on the disk. And instead of putting functions, you put here matrix Rayleigh function. And you call them phi. Boundary happens when 2 points are colliding. But since they are ordered on the disk, you cannot go all the way around. And if I do it like this, I would naively expect that answer is phi square equals to 0. However, would I be in the model I would say that phi actually phi of y phi y bar. And that is Q, that is delta. And the equation would be the equation of this course. If you think a little bit, and I'll explain it for people who will need it. This is generalized flat 0-1 connection. Zero two flat, 0-1 connection. Now let us consider the same theory and deform it with function in the bulk. If we have function in the bulk, we have the following boundary contributions. This W stands in the bulk, plus field 5 and here. And here the situation is interesting because boundary term, because I have two identical boundary terms, and they could cancel as a sum. And here I have W times 1 with matrix I squared. And it's called matrix derivation. Okay, so I told you something. If you will do particular problem, or if you are interested in particular subject from this, you may ask me and I'll explain in more detail. So for Lewis, it is this phenomenon. So that would be more interesting. Okay, there is also another thing that is surprising. I just want to mention it. If I consider type 80, and that includes symplectic form here. Then the easiest way to form boundary conditions is just to say that symplectic form on the boundary vanishes. It's called Lagrangian boundary condition. However, one may consider something more interesting. And it is still an open problem. So people did not agree on that. To put here symplectic form, and to cancel it by the following. Put here some fields phi and here field phi. And then the equation will be omega equals d phi from that term plus phi equals. And this would be called Orlov-Kapustin bracket. And people are still confused about them. At least nobody tweeted them in AKSZ language. So that's it. Now we need to decide about exam. So I will not ask these topics on the exam. It's just for you to know. We will have exam next week. So next week is the pre-stream week. So you need to think. Probably you would like to go to some lectures. So you need to organize and let me know where we can have an exam. Okay?
Here's the 1 day break between the pre-stream and the stream.
So when is this break?
July 4. Yeah, July 5th. 5th.
Oh, this is the
Sorry, July 5th is, what day is July 5th?
Sunday.
Sunday.
You see, this is one forms.
Why? So I wanted to study an example, however, I omitted this example.
Okay, so now what are these?
Some operators. So if you want to consider them as one form, you may consider them as one form. But I decided to make it an abstract set. If you want, I can continue this example. And on this example, let's find a one form omega. That is closed. Then there is a condition, then we can take omega squared. So since the matrix value, it's not zero. And now Q is d, dy. So I have this condition. So what is the meaning of this condition? I'm forming a connection. Omega plus p plus something. In the order g squared, exactly the case.
So here C2 is also a one form.
Yes. In this particular example,
Okay. So generally, this two.
this tool has a meaning in second order in G.
I see. So it contains some G alpha, G beta.
Yes. Okay, so now we will discuss poster after some short break. Yes.
For that,
Okay, so that complicated. Okay.
little bit complicated.
很快。OK。